Awesome. And yeah, so so welcome everybody. Happy last day of classes. Pretty amazing to believe that we've made it here. It's a little bittersweet to be having the last day of classes sort of in this environment where, a number of you will be watching this after the fact. And those of you who are here, of course, it's not exactly face-to-face. And yeah, you all have been fantastic students. It's been a lot of fun to teach this class. And yeah, I'm gonna miss you all after today. So our plan for today is basically to sort of continue the plan from Monday, which is to do some general review of the material that we've looked at in calculus. Today we're going to focus on that middle section of the class, and in a moment I'm going to cut over to a copy of the midterm, that second midterm, and we'll just go through it, discuss some problems that I thought were particularly challenging, particularly interesting, and or if any of you have specific questions that you'd like to cover, I will make sure that we get a chance to cover those. So if you do have specific questions that you want to cover, please let me know in the chat. Before I cut over, I just wanted to have a couple of course-related announcements. First of all, as you know, today, which is Wednesday, April 29th, is the final day to either express an interest in dropping the class or express an interest in transitioning to being graded in this credit, no credit scenario, right? You've gotten emails about this from me, from your other professors, and from the registrar's office. But as a reminder, credit, no credit is a way for you to get credit for the class, having completed the class, but not have it negatively affect your GPA. So I sent out an email earlier this week with details about potential grade projections, and you can sort of think about that, and if that grade is not to your liking, if the disruptions due to the coronavirus have negatively impacted your ability to get the grade in the class that you were hoping for, that is a-okay. That's why we have this credit, no credit setup, right? It would allow you to, again, get credit for the class without having this grade sort of negatively hurt your grade point average. So it's something I think everybody should at least consider. If you have questions about it throughout the day, please send me an email. And if you are opting to do that, I believe you owe me an email sent to me and CC'd to your academic advisor by 5 p.m. today. So just a reminder about that. At that point, looking forward, today is the last day of classes, and the rest of the semester involves a couple of study days. So Thursday and Friday are study days. And then starting on Monday, it's final exam time. Our class was originally scheduled to take the final exam on Tuesday, and I believe it was Tuesday morning, if I'm remembering correctly. So Tuesday, May 5th. I should have had this pulled up. Let me check. Yeah, Tuesday, May 5th is the date that we are scheduled to take the exam. And in this class, there will be a final exam. It'll be sort of a cumulative final exam. You could think of it, just taking all three of our tests, maybe condensing it a little bit, so pruning out some of the problems, making it a little bit shorter, but taking sort of like those questions from, or those kinds of questions from all three of our tests in a final exam setting. Each of our individual tests was designed to take like 75 minutes. The final exam will be designed to take a little less than 3 hours. I would say it'll probably be about twice the length of a in-class test. And if you were in my Calc1 class, you might remember that in Calc1, the final exam was optional, depending on whether or not you wanted to improve your old test grades. Unfortunately, that's not the case in Calc2. I had a big internal debate about this back at the start of the semester. I had another internal debate as we transitioned to online learning. But in the end, I'm asking everybody to take the final exam. Now, it does have the ability to raise at least one of your old test grades, the idea being that if you score well on the final, it will replace your lowest test grade that you've taken so far. And so as a result, doing well on the final can also boost one of your other test grades, and it has the ability to greatly, positively impact your grade. So I think this will be designed to be completed the same way that the other tests were. You can do them on your own time on Tuesday. You'll have the full 24 hours. It'll be designed to take a little less than 3 hours, but I won't be setting a strict time limit on that. So you can take it sort of as you are able throughout the day. I'd ask you to carve out sort of a solid chunk of time to do it if you're able. So not like, take an hour here, an hour there, etc. Try to take it all in one sitting if you can. But obviously these are weird times. I'm very happy to be flexible there. Between now and then, I'm gonna have a couple extra office hours, just drop in office hours to talk about anything that you all want to. Look for an email with those times. I still have to finalize that. And I think that's all I have to say as far as, no, that's not true. As far as announcements go. The final thing I wanted to mention are the quiz mastery, quiz reassessments. A lot of you have been fantastic about trying to get those reassessed or sending me emails on your progressing quizzes, getting them up to a level of mastery. Just a reminder to please continue doing that if you intend to. The final day to do that is the same as the final exam day. So that's been pushed back to next Tuesday. So by the end of the day next Tuesday, all graded material for the class will have been submitted. Great, awesome. I think that is actually the final thing that I wanted to say. Oh no, very quickly. Also, don't forget there are some extra credit opportunities, right, that are posted on Moodle. So I wanted to quick plug reminder of those. Okay, and that's it, promise. Any questions about any of that? Okay. Great, I'll take that to mean there are no questions. Let's dive into things today. So we're gonna be looking at the test 2, so Calculus 2, test 2. And actually, as a reminder, let me share my browser with you for a second. So as a reminder, test 2 was taken shortly before spring break and before everything went kind of crazy. So we took it that Monday, and that was before we knew that we would be switching to distance learning. That was before we knew exactly what the rest of the semester would look like. And so if I scroll down here, that means that I should say I never got a chance to hand back test 2 to you in person. Right? So you never got a physical copy of that back. Instead, I graded it over spring break. I scanned your graded copies of the test into Moodle, and I uploaded them in this assignment here in the March 9th to March 15th week, right? So there's Calc2 test 2. And if you go to Moodle and you go to that assignment, you should be able to find your graded test for you to take a look at. I think we mentioned this back at the start of the distance learning, but again, everything was crazy then. It's possible that slipped through the cracks. So that is where you can find your graded version of test 2. While I'm on this page, let me remind you, this is also up here is where the extra credit opportunities are. So just a reminder there. Okay. So that's where our test 2s can be found. I'm going to pull up a blank copy now for us to take a look at. And as I'm doing so, let me remind you, so test 2, there we go. Test 2 covered this middle portion of the semester where we were really looking at applications of integration, right? And these came in sort of 2 flavors, I feel like. So applications of integration, there were, I would call sort of direct applications, right? And direct applications would be those applications in which you can compute something new by setting up an appropriate integral and computing that integral. So a direct application of integration, I can integrate something or set up an integral that tells me blank. And the big sort of direct applications that we talked about, these were sort of the early skills in that part of the semester. That involved sort of area between curves. That involved average value of a function, right? So the average value of a function. That included calculating some geometric quantities, things like arc length. So we talked about arc length. We also talked about different volumes, so ways that we could measure volume. And so, in fact, volume was its whole little subcategory, right? I thought about giving it its own subcategory here, but with volume, we talked about, let's see, we had washers, we had discs, we had cylindrical shells. I'll just write shells. And then we also had cross-sectional slices. The different ways that we can compute volumes by setting up an appropriate integral. And I think that was just about all of our direct applications of integration. So explicitly computing an integral to tell us something new. We also had indirect applications, right? And so that's just, what I mean by that is I mean applications of integration that aren't just explicitly setting up and computing an integral, but maybe have some additional, I don't know, additional something that's required. And really, maybe I'm making this more complicated than it needs to be, because when we talked about indirect applications, the big thing that we talked about in that case was differential equations, right? So differential equations, these were these equations that involved functions and unknown derivatives of those functions. And our goal was to try to find solutions to these differential equations, so to find functions that satisfied them. And what we saw was that in these differential equations, we could sometimes, at least we could describe them, right? So we could describe them. Are they first order, second order? Are they linear, nonlinear? Right, so we could describe them, and in specific circumstances, we could actually solve them. And the examples that we really looked at were these separable equations, right? So we could solve separable differential equations. Finally, we talked about slope fields as a way to give us some qualitative understanding of what a solution to a differential equation might look like. So we, discussed slope fields. And despite that sort of coming in right near the end, there was a lot packed in there, right, as far as these differential equations went. So there was a lot that we could say about them. Okay, so those were sort of the big topics in this second unit, right, this sort of middle third of the semester. And test 2 really examined all of these, I think, or at least almost all of these. So yeah, that being said, let's scroll through, just see what sort of problems there are and see which problems might be interesting for us to collectively talk about here this morning. And again, I have really no agenda as far as specific problems to talk about. If pressed or if nobody says anything, I'll pick some, but I'm also very happy to take questions from you all about any of these problems or any of these topics. So just sort of starting off, we immediately jump into a question about area of the shaded region. Yeah, okay, so area between two curves. So we have this problem in which we're given two functions, the sine function and the cosine function, and we're asked to find the area between these two curves, the shaded area here. And we're not actually asked to find the shaded area. I think this is really interesting. We're asked this question: set up but do not integrate an appropriate integral or an appropriate integration that could be used to find this area. And this is a really important point to keep in mind, is that a lot of these problems, the real art of the problem, or the real creativity of the problem, was in setting up the integral. So many times, once I set up the integral, the rest of the problem just became a integration problem, which, while interesting, is not sort of the main thrust of the problem or the main important part of the problem. So our goal was to try to set something up. And so we can do this. And as a reminder, the formula for area between curves, right? Somewhere out there, someone like, and if maybe you, dear viewer, should consider making a list of all of these formulas just to sort of study in the background, to try to memorize them to prepare for this test. And so area between curves, this was always a definite integral from some endpoint to some other endpoint of the top function minus the bottom function, right? Where we had to pay really close attention to what was the top function and what was the bottom function. So top minus bottom at any given x value, like top function minus bottom function is giving us that length. And so as we integrate up all of those lengths, we end up calculating that area between the two curves. Now, what makes this an interesting question, in part, is because in this example, the function that is the top function and the function that's the bottom function are changing positions, right? So at first, and so not only is this a problem about area between curves, but it's a problem about remembering facts about our trig functions. So we want to recognize that this function, at least initially, the top function, is cosine, right? Cosine is the function that starts up here at 1, while the second function, which starts down here at 0, that's the sine function. And what we realize is that at first, the cosine function is above the sine function, but that's going to switch partway through. That's going to switch right here, right? And beyond this point, and we have to figure out what that point is, but beyond that point, the sine function, right? Maybe I'll use a different color here. Beyond that point, the sine function will be on top, and the cosine function will be on the bottom, right? Until we get to this point, and then it switches again. So for the final piece of this integral, we'll use a third color for this. So for the final piece of this integral, the cosine function is back on top, and the sine function is back on the bottom. So in fact, the integral that we need to set up isn't just a single integral, but it's going to be 3 different integrals defined on 3 different regions, depending on which function is the top function and which function is the bottom function. And so in this case, we would have to recognize that this x value, right? This x value is pi over 4. Pi over 4 is where the sine and cosine function actually agree with each other, right? That's 45 degrees. We could also see visually that that's halfway between 0 and pi over 2. So that's going to be pi over 4. I'll quickly point out this number here. That's going to be pi plus an additional pi over 4. So that's 5 pi over 4. And so our 3 integrals will be defined as follows. We'll have the first integral where the cosine function was on top. That's the purple integral. That's going to be from 0 to pi over 4, right? And that's going to be the cosine function minus the sine function. And then plus, we're going to have this second interval, which involves a second integral. That one's going to be from pi over 4 to 5 pi over 4. Let's fix that to 5 pi over 4. And that's going to be sine minus cosine. And then finally, we'll get back to this third interval. Or I guess we'll get to this third interval. And that would be the interval from 5 pi over 4 to 2 pi of cosine minus sine again. Right. So I think as far as sort of problems in this middle third of the semester went, for these kind of direct applications of integration, Area between two curves was more or less the most straightforward, just measuring top function minus bottom function. But even then, there can be some subtlety or some nuance, as this example, I think, illustrates. Cool. Any questions about that? Okay, all right. I ask if there are any questions, in part to see if there are any questions, and also in part to get a quick sip of water. Let's clear these annotations. Let's clear that, and let's keep going. So just like in Monday's class, I don't think there will be time to talk about all of these in excruciating detail, but I will try to at least point out or remind you of a lot of the formulas that are important to us as we go forward. And maybe problem 2 is an example of that. Again, if anybody really wants to see problem 2, please say something in the comments. I will absolutely talk about it. And that is no problem whatsoever. If you're thinking it, let me know. It's probable other people are thinking it and too quiet to say anything. So don't be afraid to say something. So this problem, right, asked about average value on an interval. And so whenever we had these kind of problems, the average value of a function, it was always a given function, and it was on a given closed and bounded interval of the form a to b, right? So it was on a specific range. And so the average value of g on an of this function g on this interval, a to b, well, the formula would be like this. We would ultimately calculate the integral, giving us the total area under the curve. So that would be the integral from a to b of g of x dx. And then we would multiply that by 1 over b minus a. In other words, we would divide by b minus a. And that would give us this average value. And if we wanted to give this notation, sometimes this notation is used. So g sub average. Okay, so this is the formula. And there's a lot of great intuition behind this formula. Just specifically, I'll point out that notice our function g, if it's going from a to b, maybe this is our function g, then the integral is giving us an area, right? And an area is sort of like a two-dimensional expression. So it's giving us the area of all of this. And when I divide by b minus a, well, b minus a is exactly the length of this interval. It's the length of the base, right? So b minus a is that bottom length down there. And so if we think of area as kind of like a base times height, or if we think of base times height as a model for area, then I have my area divided by the length of the total base. That's giving me some sort of height. And it is, in fact, this average height that we're discussing. In the case of a rectangle, right? So if my g hadn't been sort of a curvy function, but had actually just been a constant, right? And so my function looked like this, then this would be the height c. The total integral would become c times b minus a, and then that integral quantity divided by b minus a would just give me this average value again. Maybe I'll call that k, so the average value k. Okay, love it. So that's our most important formula here for problem 2 for average value. Moving on, we had another kind of integral that it described arc length, right? And arc length was given by this formula. It was the integral from, so again, we had a function, I should start there. We had a function, in this case it was g, and then we had a region over which it was defined, right? So here it's x equals 0 to x equals 3. I could write that in my interval notation as 0 to 3, And that's, again, just going to be some closed interval a to b. So the arc length could be thought of as the integral from a to b of a certain integral. And we derived this formula in class. It's actually low-key one of my favorite formula derivations that we did in class. Really fun, really challenging, but really good. And the answer that we got was that the arc length should be the integral of the square root of 1 plus, in this case it's a g, so it would be g prime of x. And then I'll take that g prime of x and I'll square it under the square root sign. So it was the square root of 1 plus g prime in parentheses squared. So arc length is one of those really interesting quantities, right? It's saying sort of specifically to calculate the length of the curve as if it were drawn out by a piece of rope, right? So again, if I have my a and my b, and I have a function g, right? What this is asking us to do is to literally pretend that this curve is like a piece of rope, and then if we were to take that piece of rope and pull it taut, how long would that piece of rope be, right? That's what we call this arc length measurement. And it turned out that arc length was equal to this expression here. And again, that was a really enjoyable derivation day in class, right? We constructed this sort of this approximation. We drew all these straight lines. We measured the distance of all those straight lines, right? So we measured, the length of those, and that ended up being, we used the Pythagorean theorem for that, right? So this length could be thought of as the square root of this length plus this length. This length ended up being, this length squared plus this length squared. That bottom length we called delta x. This length turned out to be related to g prime times delta x. And we could square both of those. We could factor out the delta x squared. The delta x, as we took a limit, became this dx. And then what was left over was 1 plus g prime squared, which is where those pieces came from. So that square root of 1 plus g prime squared is really coming from the Pythagorean theorem in this picture here. So yeah, just a fun day. Good times. Good times back in mid-early Calc 2. So as a result, though, we get an integral that's often really, really hard to explicitly integrate, right? Usually that's an integral where it's really hard to find an antiderivative. But we can at least, once again, set up and then not integrate it. So setting up in this case was key. All right, what else we got? What else we got? As we continue on, we're getting more into the volume measurements. And perfect, okay. So as we get into volume measurements, we're often interested in, and maybe I'll sort of write this up first. So we're interested in, first, which kind of volume are we trying to construct? So again, there were 4 of these. So there was, I'll just call this volume thoughts, things to think about when you first come across a volume problem. So things to think about are the kind of volume that you're looking at, right? So are we looking at a volume that was cross-sectional, that was measured using cross-sections? Was it measured using disks? Was it measured using washers? Right, usually disks and washers, we can sort of read that in the same sentence. Or was it measured using cylindrical shells? Okay, and often, so I would say, yeah, in thinking through these, there's a big dividing line that should be drawn between the first one and the bottom 3. Usually the first one stands out as as a cross-sectional problem because it will explicitly say in the problem some information about what the cross-sections are, right? And indeed, in problem 4, we see R forms the base of a three-dimensional object whose cross-sections measured perpendicular to the y-axis form squares, right? So what that means is, well, here's my y-axis. Perpendicular to the y-axis, I'm sort of looking in this direction, right? And so what I'm getting is that perpendicular to the y-axis, if I were to take a slice of this object, right? So I were to come down and just slice this in a manner as drawn. So I'm looking at my three-dimensional object from a bird's eye view right now. Its footprint is given by the shaded blue region, and I take sort of a downward slice into the earth in this direction. What I have here would be a square. So sort of coming out of the paper, coming out towards us, is a square of some sort. And if I try to draw that, I think I'm going to end up butchering it, but maybe something like this, right? Sort of coming out of the picture up towards us, some sort of square. Okay, brilliant. What I actually tended to draw in class, which is a little bit easier to draw, it would be to take this, sort of pull out the slice, pull it out so far that it's in a brand new, so it's not on the same axes. And what I would get was that if I pulled that out and sort of set it up to look at it from the side, it would be this cross-sectional square. So when it came to cross-sectional slices, right? Again, it usually identifies itself in the problem. It will also identify what the shape of the cross-sectional slice is, and it will identify the direction in which the slices are being taken. Is it perpendicular to the x-axis or is it perpendicular to the y-axis? In this case, it was perpendicular to the y-axis. So, right, perpendicular to the y-axis means we're hitting it at a 90-degree angle, which means our slices are going this way. Now, for cross-sectional area, the formula that we used was equal to the integral from A to B of the area of the cross-sectional slice dx or dy. Right, so one of the tricky things in a lot of these volume computations was actually figuring out what the right integral to set up was, and that includes figuring out whether we're integrating with respect to the variable y and with respect to the variable x. And so let's think through this, right? It's been a while, so let's refresh ourselves. If I am taking slices that are perpendicular to the y-axis, right? Here I'm just drawing a few in here. If I'm taking these slices that are perpendicular to the y-axis, then notice each of these different slices is, ooh, that was a bad one. Each of these different slices is resulting in a different area for a different sized square, right? So this bottom one, for example, that's a pretty teeny tiny square with a relatively small amount of area. And similarly for this one here, that's a pretty tiny square. So in fact, in this problem, the area of our squares is changing depending on the y value at which we are making the slice. So down here, this square corresponded to y equals 1, right? That was a really small square. This one corresponded to y equals 4. And this one up here corresponded to, it looks like maybe y is equal to maybe like 7.4 or something. But the point is that the area of each of these squares is changing depending on what y value we're looking at, which means in this problem, the area is a function of y. The area changes depending on which y value we look at, and so we can think of it as a function of y. And so to make this a little bit more precise, this problem would require us to integrate from y equals some number to y equals some other number. And let's look, the lowest most y value is y equals 0. The uppermost y value is y equals 8. And so this would be the integral as y goes from 0 to 8 of the area of the slices at position y. So that's just some function a of y. And we're integrating that up dy. So we're most of the way. One of the big challenges is figuring out whether to integrate dx or dy. I'm actually going to add that to our volume thoughts up here. Integrate dx or dy. And along with that, there's also this question of the bounds of integration. So what are the appropriate bounds of integration? But we saw here that we were integrating dy, and so we just went from the lowest y value up to the highest y value. And so that's great, that's fantastic. The final question for cross-sectional slices is going to be, what is this a of y? So how can we calculate this a of y? And so let's think through this. This will depend on how we are defining our cross-sectional slices, which in this case, they are defined to be squares. Now, a square, of course, has an area that we know how to compute. We find its side length, and we square it. So the question becomes, for a given square, what is the side length? Because if I can figure out what this side length is, that will be the same as this side length, and I can just square it. And so going back to the picture, the side length, right, looking at this picture here, this side length is actually going to be measured as the difference between our two curves, much like we did in that first problem, the area between two curves. So I'm measuring from this value all the way down to this value. At the example point, that becomes 2 minus 1, and so the length of that side is equal to 1. But more broadly, or more generally, when I'm looking at this expression, I'm going to figure out what that function is. I'm going to figure out what this function is, and I'm going to subtract this top function minus this bottom function, right? So I'm going to take the two lengths, or the two functions, and subtract them from each other. And that's how we're going to determine our side length in this case. Now, or I should say, one of the interesting things is that this is supposed to be a function of y. So every single y value corresponds to a different side length, which corresponds to this function, again, minus this function. But that means that we have to represent our functions as functions of y. So since we're integrating dy, right? Since we're integrating dy, everything should be in terms of y, which means that I should be describing these x values, right? So it was x value of 2 minus x value of 1. More generally, it's sort of this x value minus this x value. Those x values should be described as functions of y. And now let's think through this. We were originally given our functions in the usual form, where y is given as a function of x. So y equals 2x and y equals 4 root x. This straight line, right? The straight line is going to correspond to y equals 2x. The curved line is going to be y equals 4 root x. But we need these to be flipped around because we have to be able to express x as a function of y here. So what we'll get is y equals 2x. We can rewrite that as x equals y over 2. And this one, y equals 4 root x, we can write that as x equals, I think, y over 4 squared, right? Again, that's just solving for x in this case. So now we have our two functions, but with the x values written as a function of y. And so that distance, right, again, the distance from here to here is going to be the one function of y, that's y over 2, minus that distance, the y over 4 squared. And so this side length becomes y over 2 minus y over 4 squared. And because this was a square, this side length is exactly the same thing. Okay, so what is our final integral then when all the dust settles? Right, well, we have most of it already. It'll be the integral as y goes from 0 to 8. The area then is going to be the expression y over 2 minus y over 4 squared, quantity squared, right? So the area is just the side length times the side length, is just that side length squared. And so the area becomes that quantity squared dy. And now, thankfully, this was a problem where we just had to set up the integral, not actually integrate it, so we can leave it like that. So, pause there and see if there are any questions. I think these kind of volume problems ended up being some of the most challenging problems that we looked at back in this moment in the semester, back in this middle third. So the volume problems were always a challenge. Any questions about the problem that we just looked at? All right. Okay, if everybody's doing okay for the moment, let's see what else we can talk about. Okay, so what we have next are a couple more volume problems involving disks and washers. I want to talk through, I think, disks, washers, and shells, I should say. I want to talk through at least one shell and one disk/washer. And let me think through exactly which ones would be the most valuable. Oh, okay. Actually, I remember going forward, there's actually a few that I do want to talk through. Let's talk through problem 6, because it explicitly asks us to use the method of cylindrical shells. So we don't have to think too hard about which method to use. We can just use the cylindrical shells. And cylindrical shells were sort of a weird one. Let's remember what they look like. Okay, so first I have these functions, y equals arcsine of x. That's this curvy function here. We have the line y equals pi over 2. I think that's going to be this line right here. And the y-axis, of course, is going to be this line. So we have the shaded area that's between those three curves. It's pictured in the picture. Our goal is to use the method of cylindrical shells to calculate the volume of the object created by revolving this region about the x-axis. So here's our x-axis. This is going to be our axis of rotation. So we're going to sort of highlight that axis, and we are going to rotate this region around that axis to create a volume of rotation. Now, when creating a volume of rotation, the big question is, do we use cylindrical shells or do we use disk/washer? And the choice of which one we want to use determines our cross-sectional slices, right? So going back to our list of volume considerations or volume thoughts, when it comes to this distinction, washer versus shell, we have to recognize that the two different ones will give us two different directions for our cross-sectional slices. If I were to use disk/washer, I would create cross-sectional slices that were perpendicular to the axis of rotation. So I would sort of draw them in this direction, right? That's for disk/washer. And the idea is that as I took that line perpendicular to the axis, and then I rotated it, right? Maybe I took a line perpendicular to the x-axis and then I rotated it, I would be tracing out a disc, right? Or a washer. Think of it as sort of like a very flat circle, like a vinyl record or something, or a CD. And so that would guarantee that we are taking cross-sectional slices perpendicular to the axis of rotation. However, if we're asked to use cylindrical shells, we will want to take cross-sectional slices that are parallel to the axis of rotation, right? So now if I take, I should have just used my pen. If I take something that's perpendicular to the axis of rotation, and then I revolve that, it's going to trace out like a little penne pasta or a little cylindrical shell. It's going to be sort of flat in this direction, and it's going to be circular in this direction. So we'll end up with a nice cylinder as our answer, right? And so our cylinder, as it gets rotated, will look something like this. Now, so that's going to be our cylinder. And let me go ahead and pull that out, right? I guess I'll actually keep it with the same orientation as it is here. So we'll draw it like this. Okay, and then in the middle, here's our axis of rotation. Real artistry going into these pictures. So that's going to be our cylindrical shell that we're looking at. And the question becomes, how do we integrate this up? Well, the idea behind cylindrical shell integrals was that we took an integral from a given point A to a given point B of the area of the shell times a d, and then again, x or y, depending on the situation. So really, this formula looks very, very similar to the volume formula for cross-sectional slices. And spoiler alert, it's very similar to the disk as well, right? That would just be the area of the disk or washer in the case where we're looking at those. So all of these formulas are kind of similar in the sense that we're integrating up a certain area. But of course, the area of the shell, right? This is sort of the surface area of this penne pasta. That is different than if it were the area of a disk or the area of, say, a square. One sec. Excuse me. So the area of a shell, right, or the area of a cylinder is actually given by, sort of write this in red here, it's given by 2 pi times the radius of the cylinder, and here's the radius, times the height of the cylinder, and this distance is the height. Right, so again, imagine the cylinder sort of turned on its side, but if you tilt your head 90 degrees to look at it, the radius is just the radius of the circle, while the height is the height of that perpendicular direction. Right, and so this is the formula for surface area of a cylinder. Perfect. And so that is what we will be integrating. Now, let's focus on this question of dx or dy before we explicitly compute the r and h values. So notice the cylinder that I drew corresponded, because I was looking at this perpendicular, or I'm sorry, this parallel to the axis drawing, this corresponded to a given y value. And so you could think of this cylinder as corresponding to the cylinder created at that y value. And if I looked at a different y value, right, so say like this y value, I would get a different cylinder. It'd be a teeny tiny sort of skinny cylinder like this, right? And that's what would happen if I looked at that y value. And if I looked at a different y value, like up here, I'd get a really big cylinder. And so we see that we're getting different cylinders of different sizes, right, with different radii and different heights, depending on which y value we are looking at. And so in this picture, if I'm integrating using cylindrical shells and with an axis of rotation that is the x-axis, I would want to integrate dy because each of my cylinders is changing depending on my y value. And so that helps us determine not only which way are we integrating, but also what the bounds of integration are. If we're using y values, we want to integrate from 0 up to, in this case, pi over 2. So y goes from 0 to pi over 2. And then what we're going to integrate is the quantity 2 pi times this radius times this height. And let's try to figure out what each of those are. The radius is going to be the distance from the axis of rotation to the line that we're drawing that generates the cylinder, right? That's going to be this distance right here. And that distance at a given y value is literally just y, right? Think about it this way. Whoops. Think about it this way. If this y value was sort of at the halfway point, right, and I was up to, say, pi over 4, then that radius would just be equal to pi over 4. In general, for our given y value, the distance from y to the x-axis is exactly y. So that is our radius in this case. The height of the rectangle, or the height of the cylinder, is going to be the length of this line right here, right? And let me clean up this picture just a tiny bit, erasing all of that. Okay, so the height is going to be just this height, and that's given by the distance from the y-axis up to this function itself, right? And so this was the function y equals arc sine of x. That distance is going to be the distance from the line x equals 0 up to x equals this curve. And so once again, I have a function involving y as a function of x, but I need to rewrite it as x is a function of y. And in this case, x is equal to, if y is equal to arc sine of x, then x is equal to sine of y. And so what we really have then is that we are taking the curve all the way from this point, and that was x equals sine of y, all the way down to this point, which is just x equals 0. And so that distance, that length, becomes sine of y minus 0, and that's the height of our cylinder. So we can just write that as sine of y. And then we're done. So our integral here for using cylindrical shells is the integral from 0 to pi over 2 of 2 pi times the radius y times the height sine of y. Any questions about that? All right, cool. If there are no questions, let's jump down to another volume problem. And now I'm keeping an eye on the time. We have about 20 minutes left. Thinking out loud, I don't think that is quite enough time to do the next few volume problems that I wanted to do and do justice to differential equations, which were the final few problems on this test. So in the interest of consistency, I guess, or in making this a self-contained quality lesson / video recording, I'm going to try to just focus on these volume questions here. And I think we'll probably be able to answer 2 or maybe 3 more volume questions, at least 2. And I'm thinking of the 2 that I want to talk about. And we'll save differential equations to be reviewed in additional office hours or something like that. Again, I think if I tried to do both, I'd end up doing a poor job of both of them just due to time constraints. So I'd rather do a really good job at volume and then do a really good job at differential equations down the road. So let's take a look. I'm going to jump down to number 8 for a second, because number 8 is going to be a disk or washer. It turns out to be a disk problem that is, I think, really interesting, worth talking about, and throws in some ideas from the first test that might surprise us. Then I'm going to circle back to problem 7, in which we do not know whether we want to use disks or washers. And so I want to talk through sort of the thought process that goes into that. Okay, so problem 8 first, though. So problem 8 deals with this object called Gabriel's horn. This is a great, really fun math object to play around with. If we'd had a few extra days in the semester, I would have introduced this in class. But because of the time constraints on the semester, I ended up introducing it here on the test. So Gabriel's horn is a mathematical object, sort of theoretical object, that's created by taking the curve y equals 1 over x. And so, you know, y equals 1 over x, a formula that we all know and love, kind of looks like this. Right, so we take y equals 1 over x. We start at x equals 1. So I sort of start there. I go off to infinity in this direction, and I ignore the part to the left of 1. So I erase that. And I get this curve, sort of infinitely long curve, which I then revolve around the x-axis, right? And the result after I do that revolution, and I guess here's the revolution, the result is going to be exactly what we see in this picture over here. So the question on the table is whether or not Gabriel's horn has a finite or an infinite amount of volume. In other words, if I try to compute the volume of this as a surface of revolution, what would I get? And so to do that, again, it's not really explicitly told to us how we want to go about doing this, but let's think about this. We can either use cylindrical shells, or we can use disks/washers to construct this. I'm going to highlight, this is my axis of rotation. And again, the disk or washer will have a different cross-sectional slice that gets revolved than the cylindrical shell. So the cylindrical shell, if I were copying the same problem that I had done previously, right, the cylindrical shell would take a line parallel to the axis of rotation. So it would take a line like this, and it would revolve. I guess I actually have the picture here, right? So it would revolve to construct a cylinder, kind of like this. That's not as good of a picture, but we would get a cylindrical shell like that. A disk would ask us at a given, not a given y value, but at a given x value, to make a cross-sectional slice that is perpendicular to the axis of rotation, and then revolve that to get a disk, right? And so we see here that it looks like the disk picture is a little bit simpler. And indeed, if I were to pull this disk out and examine it, it really is just a disk. And it's a disk of a given radius, which we'll compute in just a moment. Now, for the disk method, right, for the disk method, the formula for our volume by disks is the integral from a to b of the area of the disk times d, well, not times, but, you know, integrated dx or dy, right? Again, very, very similar to our other volume formulas. And while I'm at it, I would say if this was a washer, then the washer formula would be the integral from a to b of the area of a washer, dx or y. So this picture is a disk, and it's a disk of a given radius r. And we know that the area of a disk is really just the area of a circle, and that circle has area pi r squared. So we can really deduce this even further to a to b, pi times the radius squared dx or dy. So at the moment, it looks like we can make certain slices that result in disks. Can we figure out what the radius of the disk is? And the answer is yes. Notice, first of all, different cross-sectional slices at different x values will give us different radii. And the radius is going to be from the axis of rotation, that's x equals 0. I'm sorry, that's y equals 0. That's the x-axis, up to the curve y equals 1 over x. Right? So this, this line, this radius, is just the line from y equals 0 up to y equals 1 over x. And so that radius has length 1 over x minus 0. And so because we can establish this, it now makes sense for us to think about using the disk method, letting the r equal this length, 1 over x. And therefore, because we have different disks at different x values, integrating dx. So these r values, sorry, I'll do it down here, integrating dx. So these r values are kind of like 1 over x. And so we end up with this new integral. It's going to be pi, it's going to be 1 over x squared dx. Now the tricky bit is to think through what the bounds of integration should be. We're going from the first x value all the way up to the last x value, but problematically there is no last x value. So it makes this kind of an interesting problem. I mean, it's all interesting, but one additional thing that makes it interesting is that we actually need to create an infinite limit or an improper integral here. This is supposed to integrate from x equals 1 all the way up to x equals infinity, which means when it comes time to calculate this, we need to use improper integrals. And so really quickly, this becomes the limit as, well, let's say as b goes to infinity of the integral from 1 to b of pi times 1 over x squared, that's just x to the negative 2 dx. Inside the limit, I can explicitly compute this because this is just a integral. So limit as b goes to infinity. The pi will stay the same. I'll actually pull the pi out so I don't have to worry about it. The x to the negative 2 becomes a negative x to the negative 1. And so this becomes a negative b to the negative 1 minus a negative 1 to the negative 1. And when the dust settles, so that's still a limit as b goes to infinity, pi times, this is just 1 minus 1 over b. And in the limit, the b in the denominator goes to 0. I should say the b goes to infinity, so the 1 over b goes to 0. And in fact, this Gabriel's horn, this infinite horn, has a finite amount of area, finite amount of volume. The volume is exactly pi, which I just think is super cool. So a fun problem, the disk method, we can implement it here without too much difficulty. And then the extra wrinkle or the final piece of final consideration is that we have to take an improper integral here to integrate all the way up to infinity. Any questions about this problem, Gabriel's horn problem? All right, we got a quiet group of you today. Let's conclude. We've got a little under 10 minutes left. Let's jump back up to problem 7 in which we're trying to revolve this blue shaded region around the line x equals 4. And the question is, first of all, do we want to use washers or do we want to use shells, right? Washer/disk or shells. So that's question number 1. And then question number 2, what will our integral be if we do this? So here's our axis of integration. Right, so we'll be revolving that entire region around x equals 4. And now the question is, which method makes the most sense? This one is a fun one because it doesn't explicitly tell us. We have to sort of think through. And really, either one could work, but one of them, we'll see, will be much, much, much easier. Let's start with disks. If we wanted to revolve, or if we wanted to create disks, we would have to create slices that were perpendicular to the axis of rotation. And that means that my slice would kind of look like this. So that would be the object that I revolved. It actually wouldn't be a disk, it would be a washer, right? And as I revolved, I would get this washer shape. Forgive the terrible picture. But I would get this washer shape that, if I pull it out, will end up looking like this, right? It'll have some outer radius and some inner radius, and the area that I care about is this donut region, this annulus region, that corresponds to revolving this line segment, which should really be this line segment, and revolving that around the axis of rotation. So the formula here is exactly what we said before. It would just be the volume of the area of the washer integrated from this y value up to this y value. But we would have to recognize that this would be an integral involving y. It would integrate from y equals 0 to y equals 2. And we would need to figure out what this outer radius is. And now let me clarify. I'll do that in red. The outer radius is that entire distance there. So that's really this distance all the way to the center of the circle. We'd have to figure out what that is, and then minus, we'd have to figure out what this inner radius is, right? And so that's going to be just that inner piece right there. And that's actually really challenging. We have this function, right? The function that's given to us is the function f of x equals 2 minus x minus 2 squared. But I would need to write this as a function of y. I'm sorry, I would have to write this, as a function of y, meaning I currently have it y equals a function of x. And I would have to turn that into x equals a function of y. And not just one function of y, I would need, for this given y value, I would need to figure out what that x value is as a function of y, and what that x value is as a function of y. And that seems like a huge pain. It's doable, but a huge pain. Yeah, doable, absolutely doable. And you all could do this, but I don't want to make you do that. Let's see what would happen instead if we used cylindrical shells. So we have the same setup in the sense that we have the same picture rotating around this axis, but instead of making perpendicular slices, we want to make parallel slices. So slices that are parallel to the axis of rotation. And in this case, the axis of rotation is vertical, which means that these slices are vertical, and they correspond to different x values, right? So for a given, ooh, that was terrible. For a given x value, we're going to create a cylindrical shell. You know what? For a given x value that's strategically chosen to be closer to the axis of rotation, we're going to construct a cylindrical shell with a certain height and a certain radius. And then we will integrate over our x values. So x goes from this point to this point, and we would have to try to figure out what those are. And that's actually harder or easier said than done. That's harder than I initially meant it to be on this problem. Let's say I'm going to call this A, I'm going to call this B, and let's just say the integral as x goes from A to B of 2 pi times the radius times the height. And it turns out that even though cylindrical shells have a more complicated formula, it is easier to calculate this radius and calculate this height. It is easier to do that than it would have been to try to use the washer method. So notice the radius is just going to be this distance, the distance from the number x equals 4 to the number x equals x. So that distance in total has a length of 4 minus x, right? 4 minus x gives us that distance. So the radius in this case is 4 minus x. And the height, well, the height is just going to be from height of 0 up to the height of f of x, right? And so it's going to be that height of f of x, so that's just going to be 2 minus x minus 2 squared. And when we tie that all together, we end up with a nice formula, which we don't have to, again, we don't have to compute this integral. We can just leave it like this, but 2 pi times 4 minus x times 2 minus x minus 2 squared. And that's it. Okay, so unfortunately, we are just about out of time. It is 9:15. So yeah, closing remarks, closing thoughts. I guess just to say, it's been so much fun having you all in this Calc2 class. It was a shame as we transitioned to this online learning environment that we lost a little bit of the dynamic nature of the in-class, experience that we had. You all have been an absolutely fantastic class, and it's been tremendously fun to get to see you at 8 a.m. Monday, Wednesday, Friday every morning. Especially while we were on campus, you all did a fantastic job of showing up, of being reasonably awake, reasonably excited as one can be for anything at 8 a.m. Yeah, keep up the amazing work for just another week. Keep working hard. Take the time to email me about these progressing quizzes or any reassessments. Study all of this older material, study some of the more recent material as you prepare for the midterm. Keep an eye out for an email from me about special office hours. Good luck and have fun on the final. And I hope to see you in a future math class, right? You've sort of seen that there's a lot of depth that we can explore here in Calc 2, and sort of that excitement and that weirdness of the things you can do mathematically only grows as you take future math classes. So I hope you're able to take more math classes in the future, and I would love to see you in a future class of mine. So yeah, thanks so much, everybody. Have a great rest of your day, and I will see you all sometime in the future.